This hour we are going to introduce a new algorithm, which is support vector machine, and also it is algorithm for classification. The output of SVM should be a binary value. So here we define it as +1 and -1. Okay, and inspired by logistic regression. Okay, I think this figure. Inspired by this figure and some mathematicians, they believe that if you want to class two different samples, okay, so that is y equals 1 and this part is y equals 0. In logistic regression, they believe the most important thing is to find this specific boundary line, and in logistic regression this line is the probability of the probability of y equals 1. Okay, the probability of y equals 1 conditioned by certain feature. And the important thing is that if you can find this line equals 0.5, and we can divide the entire feature space into two subspace, and one part, which is right here, all those data points falls into this subspace, and their classification result of linear regression is y equals 1, and the other side is 1 equals 0. So we don't really have to calculate the probability right here. For example, that is 0.4 and that is 0.1. We don't really need to calculate such kind of value to determine which category that those data point falls into. We really need, what we really need to do is to find this boundary line. That is good enough for classification. And I think another reason is that for linear regression or logistic regression, we are trying to find a line or find a curve to fit the data point. But there are some data point, for example, right here. Okay, no matter, you have to go over all the entire data point and fit those data point in your model. Okay, in your model to find the best fitting line. But for the perspective of from the perspective of linear regression, for support vector machine, they think the most important thing is that there are some data point which is right here. Okay, right here. The most important job of an algorithm is to carefully and precisely divide those points into two classes. You really don't need to handle the data points which is far away from the boundary line. So no matter how many data points right here, it really doesn't matter. But from the perspective of linear regression and the logistic regression, they have to consider all the data points, because they're their evaluation function, which is MSE or like maximum likelihood, they have to consider all data point. But but SVM does not do so. Okay, so let's take a look at the concept of support vector machine. Okay, currently we have two set of data points, +1 and -1, and here's an example. Okay, we have two features like right here, and for example two different colors of data points. Okay, one is one is +1, and the other is -1. Okay, so of course you can draw any line, right? Draw any different kinds of line to separate these two data set, but which line will be the best one? The problem is very similar to MSE. Okay, we need to find an evaluation function to help us to find the best boundary line. And the concept of MSE is to find the minimal error, right? But in SVM, it is a little bit different. Okay, we first take a look at this one. Okay, we take a look at this one, the green line. Okay, if the green line right here is the boundary line, so basically you can find another line, okay, which is right here, and you push this line to one class, and here is another line. These two support lines, okay, one of the support line will touch the data set on the one side, and the other support line will touch the data point on the other side. Okay, from humans' perspective, okay, if you take a look at the green line, red line, and the blue line, we think, okay, or we believe the green line will be better, is the better one to divide the space. The reason is that if you draw a width between this support line, and we can figure out that the width of these three lines and the green line, the width of the green line will be larger than the other two. And human beings believe that the green line will be the better one. So that is the concept of SVM. We are trying to find a boundary line which can depart these two sets of data points, and the width of this boundary line will be the largest one. So the next problem is, how do we model such kind of concept? Okay, so that is the concept of SVM, and the points right here, okay, which support us to find the boundary line, right? So these data points are called support vector, because it is a two-dimension space, right? So every point right here, it can be presented as a vector, right? So these three data points are called support vector, and sometimes we call it SV plus, but because it is on one side and the other side is called SP minus. Okay, so that is, so here is how we model such kind of problem. So basically we have two features. Okay, beware of that there's no Y in this surface, okay, because the color right here is, for example, the color right here is represent the Y value. Okay, so that is the x0 and x1 surface, okay, space. Okay, so assume the boundary line is like this, and you know, if it is a two-dimension space, if you want to draw a line, it should be y equals ax plus b, right? It should be, looks like this, but there's no y, so we basically it should be something like this one. And because it is we want to use vector to represent a line, so it is how you use vector to represent a line in the space. Okay, So basically, it may looks like the x right here. Actually, it is 2-dimension. And the w right here is the coefficient, okay? So if you multiplex these two vector, the result will be a line. The representation of a line will be looks like this. Okay, so that is a line. And because we have two support line right here, right? So basically, you simply just add a new intercept value right here and right here. Because it is a width, right? It is a width right here. So basically, the boundary line divide this width evenly. So one side is minus delta, the other side, the interception, is plus delta. Okay, so in this case we can divide this 2-dimension space into two different parts. Okay, one part is that the value is larger than 0, and the other part is this value less than 0. So that is how we use some notation to formulate this space. Okay, so the next part is that. So next part is that because we have so many parameters in right here, right? We have w, we have b, we have delta. So for simplicity, okay, we in this surface we divide all the parameters by delta. So it becomes w t transpose plus x plus b equals 0. We divided everything by delta. Okay, so but it really doesn't matter because that is just a coefficient, right? But for this part, if we divide everything by delta, okay, and this intercept becomes +1, right? And it really doesn't matter what. It really doesn't matter how did you represent the coefficient. So we can transform, we can divide everything by delta so that we can use only w, which is the coefficient, and b, which is the intercept, to represent the model. Okay, so in this case we only need to use these parameters and lines to describe our problem. Okay, so and again, how do we find those width? So the first thing is that since it is a line, right? So the coefficient right here, the coefficient of x, no matter x is a one variable or a multi-variable, the coefficient right here is exactly the tangent line of this boundary line. So it's right here. So you have to think this problem by using the vector. So w vector is exactly this pink line, the direction of this pink line. Okay, so next thing is that we pick one of the data point of x minus, which is the support vector, in one side, and the other is x plus, is another data point, another support vector on the other side. So here we have a vector of x minus and x plus, and you can see that is the black line, black direction. Okay. So next, if we project the black vector to the pink vector, and so that we project it, so right, we project it, so the length of the projection is exactly the width between two support lines, right? So we can use W transpose to find the corresponding tangent line. It is the pink one, and we use x minus one of the support vectors and the other support vectors x plus to find the black line, and we project the black line to the pink line, and the width of the projection is exactly the width we would like to find. So that is how we model these things. So if we can write down the equation of the width, we simply just maximize the width. Okay. So that we can find the coefficient, which is the W and B. So that is the math. Okay. So the width is the projection of these two vectors, and so on and so forth, so on and so forth. Okay. So the result is we are trying to find this value. In order to maximize this value, we simply just find the minima of this W vector. Okay, so we simply just find this one. And however, we have some mathematical problems right here, so it is a little bit difficult for us to understand this Lagrange multiplexer method. So we'll skip this one. If you're interested in how to solve such kind of things, you can take a look at the Wikipedia, but we will not go over this algorithm, these mathematic tools in this class. So that means we have some method to help us to find the minimum value of this W vector. Okay, we have these things. So so I think that is this part. Okay, that is how we find this value. Okay, so in this case, okay, we simply just represent the width. Okay, we would like to minimize the width, right? It is a function of x0, x1, and a b, and w0 and w1. Okay, the width is a function of all x, all parameters, and all the data points. Okay, so again, we already know x1 and x0 because we have all those data points. So it is basically very similar to MSE. Okay, we put all the x0 and x1 in this function, and it will be a function of all the parameters. When we minimize the parameters, we can use some mathematical tools to find the parameters. And again, you can still use gradient descent to find the minimum value of this specific function. Okay, again, you can use some mathematical tools or gradient descent to find the minimum value of this value. So again, we can still find what is the B star, W0 star, and W1 star, which can have the maximum width, or that should be the max, right? It's the same, but we don't talk about those statistics tools or mathematical tools how to find this thing. But just imagine that you can still use gradient descent to find the minimum value of what you want, the maximum value of the width by finding the best optimized B star W0 star W1 star. So again, usually we don't do those math by ourselves. So simply we just use some Python packages to help us to find the solution. That is enough. And I would like to introduce a new data set which is called KDD Cup 99, and we can see that it is a very which is again it is a very interesting data set which is related to cybersecurity. And again, here's the columns which is the features. Okay, it has 40 features, and we select 2 of them again as our x0 and x1, and here is the y. And we simply just use some tools, okay, which is called SVC, support vector classifier. Okay, and there's a parameter right here is the kernel is linear. We will talk about different kernels in the next week. Okay, we'll talk about it. And you simply just put all the x0, x1, and y to the solver, to the support vector classified solver, and it tells us, okay, that is the result. A line, okay, that is the W0, W1, and that is B. It's very simple, very similar to linear regression and logistic regression. Okay, and by the way, it tells you what is the index of the support vector. Okay, we have a lot of data sample right here. It tells us like the number 240. It is the support vector. Okay, and here is the x0 and x1 of the support vectors. And you can see that in a very complex example, there will be lots of support vectors, not only 1 or 2, because many vectors will be on the supporting line. Okay, so here is it. Okay, and so that is support vector machine. Okay, you can find a line. You can separate the data points into 2 different classes by using the boundary line, and I think that is good enough. We will teach you how to use support vector machine in Orange next week. Okay, so the next topic I want to talk about is classification report, because let's take linear regression and SVM, for example. They are both algorithms for classification, but the concept of them are a little bit different. Okay, logistic regression is trying to find the fitting line, which is a sigmoid fitting line, right? And SVM is trying to, so that is y, that is x, but SVM is a little bit different, right? We're trying to find a boundary line. Trying to find the boundary line. So basically, the concept of the algorithm is different, and the way they find the best model is different. That is, logistic regression use maxima likelihood, right? And the SVM use the widest width, right? So that's basically that different, but they both binary classifier. So it is a little bit difficult for us to evaluate which algorithm is better than the other one, especially you use different algorithms like linear logistic regression and SVM. So we need a unified way to classify to evaluate different classifiers. So here is the classification report supported by Scalar. You simply just put all the X and Y in a classification report. It gives you a report like this. But how do we understand the value right here? So the first thing I would like to talk about is confusion matrix. Okay, so I have so here we have a better class node right here. Okay, is the method we introduce is confusion matrix. It is a method to help us to evaluate different classifier. Okay, let's take a binary classification for example. Okay, sorry, the target is either 0 or 1, okay, or -1 plus 1, which is okay. Okay, and we have n data points, right? So actual, okay, left hand side is actual, that is detection. So we can we have n data point, right? So we think about one thing. For a model, the model is for prediction, right? So how many data points out of n that its actual target value is 0 and the prediction result is also 0? So there will be something right here. So that means out of n data points, okay, there will be some data point, its actual value, y value, target value is 0 and your prediction is 0. So that means you do a right prediction, right? The other part is right here. That means the actual value is y equals 1 and the actual prediction is still 1. So that prediction is still the right prediction, right? So we put the how many data points in this cell and this cell, and this cell, it has a name which is called true negative and true positive. It's right here. Okay, so in these two cells, you do the right thing, 0 to 0 and 1 to 1. But you know sometimes we have misclassification, right? So in this cell, it indicates how many data points out of n that they are actually 1, but the prediction of your model says it is 0. So that is called false negative. And the other part is false positive, which is the actual value of the data point is 0, the y value is 0, and your prediction is 1. So the red cells, they are wrong prediction, right? So you know a very good model, the value in the green cells should be large, right? A bad classification model, their red cells, the number of in the red cells should be large. So that is how we use confusion matrix to evaluate different classifiers, right? So of course there are some other values we can calculate. For example, accuracy. It is very straightforward, right? So that is okay. We have the red part, we have the green part, and we divide the green part by all the data points. So that is how many. What is the ratio you have right prediction? So usually accuracy is the best, is the straightforward and the best. I think it is the best one of the way to evaluate different classifiers. And of course, mathematicians they invent a lot of different metrics index to help us to evaluate different models. But we will talk about those things later. And here we have a value called f F1. That means it is even more complex. Okay? But in modern analysis, usually we use F1 and the accuracy to evaluate the efficiency of different models. The higher the better, right? The higher the better. And but before I continue, I would like to talk about some important things. Is that most of the time when we create a model, the goal of our model is to find the best MSE value, the best width in SVM. But when we evaluate different classifier, we use another way to evaluate accuracy, to evaluate different models. For example, accuracy. It is not necessary that if you have a best MSE value, it indicates you have higher accuracy. No, it is not correct. Sometimes the best model which has better accuracy, it is not necessary to have a highest, the largest MSE or the highest width, because these two equations different, right? But we believe that if we have a better MSE, we have a better maximum likelihood, or if we have a better width in SVM, it should imply that it has a better accuracy. But the actual situation is not like that, because those equations are different, right? Okay, that's the first thing. And the second thing is that for different applications, it is not necessary for you as the analyzer to find the best accuracy model, because accuracy is not everything. Let's take the medical problem, for example. If the y equals 1, okay, if it means cancer, so we can collect n patients, and we create a model, okay, and we use some mathematical tools to help us to predict if this patient has cancer or not. Okay, so 1 is has cancer, 0 means no cancer. Okay, from the perspective of math, okay, from the perspective of math, we like to find a model which has the high accuracy or high F1 value. But the medical application is a little bit different, okay? Think about one thing. The false negative in mathematical application, that means the patient do have cancer, but your model, your predictor, says the patient has no cancer. And that would be a very, very severe problem of this model. Again, the patient actually has cancer, but your predictor says no. Right? It is a very severe problem, right? Okay. And for this part, false positive means the patient has no cancer, but your predictor says he or she has cancer. It is scary, right? You don't have cancer, but the predictor says you have. But for medical application, you can simply find some other models or some other medical tools or some other whatever to check again if the patient has cancer or not. So that means it is scary, but this false positive in mathematical application means it is scary, but you can still have some second opinion or some other tools to help you to check against the result. Sometimes some other tools may say, okay, you actually don't have cancer. It is just a false positive of your model 1. So it is okay to have false positive for medical application, but it is very severe. It is a severe problem to have false negative in mathematical model. So sometimes we are not pursue the high accuracy. Sometimes you need to consider different applications. Sometimes high false positive is okay, but you would like to have a low false negative for some situation. So if you have high false positive and low false negative, your accuracy will not be the highest accuracy, right? Okay, so let's take a look at this figure. Okay, so we have two classes. Okay, the blue one and the purple and pink one. Okay, so that is the distribution of these two classes. Okay, we have some data points right here. So if you have a model, okay, so that is for example x1, okay, that is the count. Okay, count. Okay, so if you have a model, okay, and it create a boundary line, no matter what kind of model you have, it create a boundary line right here. So as we can see that some blue point which falls under the boundary line, right? So the data point, the blue data point under this area, right, is misclassification, and some pink data point which is above the boundary line, and again they are also misclassification, right? So the pink part, this part is the false positive, and this part is the false negative. Okay, false positive means actually it is 0, but the prediction is 1. Okay, the false negative is the opposite. So sometimes we believe the model, which is right here, the black line right here, it may have the best accuracy. The model would like to have a smallest misclassification area, right? So that the model has the highest accuracy, because accuracy is the false negative plus false positive plus true positive, true negative, true positive, true negative, right? And right here is the true positive, okay? And the pink right here, that is the true negative. So if you want to have the highest accuracy, you have to minimize these two parts, so that we have the highest accuracy. But as we mentioned, it is not necessary for your application to find the highest accuracy. Sometimes we will move this boundary line, okay, to either side. Okay, take this for example. If we have a new boundary line, for example, right here, okay, right here is a new boundary line. And as you can see that the area of false positive become larger, right? And the area of false negative become smaller. So basically you can move your boundary line to adjust the how many false positive or how many negative you would like to have, right? But if you move the boundary line, the accuracy will not be the highest accuracy. But again, as I mentioned, it's a application. You can move it. Okay. So let's take a look at this figure. So let's take it. That is false positive, right? That is true positive. So when you move, your boundary line, okay, your false positive rate, okay, and true positive rate will change with respect to where you put your boundary line. Okay. Let's take a look at this very strange boundary line. If you really move your boundary line to here, to the green line, and you can see that all the positive sample, which is the blue ones, will be correctly classified. So your true positive is rate will be 100% because every blue dot will be classified as blue because they are at the right hand side of this boundary, green boundary line. But as you can see that if your true positive rate is 100%, that means your true negative rate, which is the pink data point at the left hand side of the green boundary line, will be very, very small. And you misclassify lots of pink data points. Okay, so that is one thing. The other thing is that if you move your boundary line to the right hand side, and that means you can classify all pink data points, which is the true negative rate, is 100%, because you can correctly classify all the pink data points to pink class, because it is at the left hand side of the blue boundary line. And again, you can see that now your true positive rate will be very small because most of the blue data points are misclassified because most of them are not at the right hand side of the blue lines. Right? So if you move your boundary line, take this for example, you can see that if you move your boundary line, your false positive rate, your false negative rate, will changes correspondingly. So here is how we describe such kind of things. Okay, this data point. Okay, this data point right here, the bullet point right here means you have a very, very high false positive rate, and at that moment you have a very high true positive rate because you classify everything to 1. So you missed everything. Every pink, this one is, you missed every pink data point, but you can correctly classify every blue data point. And right here, this data point, that means you have no true positive rate and you have no false positive rate. That means you classify everything to pink. So you have any blue point which is classified into blue class, right? So your true positive rate is 0. And meanwhile, your false positive rate is 0 as well. So I think and again, I think most of the model would not do such kind of things. So basically, they simply just adjust their true positive, their boundary line in the middle. So you can draw this line, and we can see that in the previous example, you can simply just draw a line right here. Okay, 54 degrees, 45 degrees, and it may touch certain data point right here, and that means this point might be the best boundary line you should select, but it has a very high true positive rate. It can correctly classify y equals 1 data point with y equals 1, and it has a very low false positive rate. Okay, so that is I think that is the sweet spot of your boundary line. If you move your boundary line from the right hand side over to the left hand side, and it has corresponding false positive rate and false true positive rate. And for sometimes we will draw this curve. This curve is called ROC curve of a model. If you move the boundary line in the model, okay. For sometimes we will draw different models in the same figure, ROC curve, and it will have different shape. Then how do we evaluate different models if we have their ROC curves? Again, you simply just draw a 45 degrees lines, and it touches the model, right? It touches the ROC curve of your model, and that is the sweet spot of the boundary line of each models. And the point which is close to the up depth side, and that is the better model, because with a smaller false positive rate, its true positive rate would be higher. Or you can simply just draw a line like this. Okay, with the same false positive rate, and the blue line has the highest true positive rate. Okay, so that is how we evaluate different models, classification models, and we will teach you how to use orange to to find this figure next week. Okay, so and again we will talk about different version of support vector machine next week. So I think that's all for this week. Okay, thank you.